Hello everyone, I will introduce our work, Challenges from Faster Camera Motion and Image Blur Dataset and Evaluation. I'm Junjie Zhu. The aim of this work is to study the impact of the camera motion speed for image and video-based tasks, as those tasks are affected by the quality of images, while the image motion blur induced by faster camera motions is a common factor that severely degrades the image quality. Below are object detection results on two images, blurry image and its corresponding sharp image. It is obvious that the image blur degrades the performance of object detection. A dataset that provides image sequences with different camera speed is required for the study. And also, those image sequences should be recorded in the same scene with exactly the same camera trajectory so that we can measure the influence of the camera speed or image blur for an approach of some kind of tasks. Also, same images with sequences with different camera speed should be captured at same precision and their blurry degrees are different. However, it is rather difficult to make this kind of dataset in the real world. Therefore, to make a dataset that meets the above requirements, we propose a method to synthesize image sequences based on real captured sequences. The only difference between the synthesized sequences and real captured sequences is the camera motion speed. The synthesized sequence will have faster camera motion speed than the real sequences, and the image in the synthesized one will be blurred by the faster camera motions. Then, based on our method, we make a synthesized dataset. We then evaluate several mainstream methods of two tasks. SLAM and image deblurring on our dataset, and study the performance of those methods with different camera speeds and image blurs. Let me introduce our synthesized method. We first record original image sequences in real world with slow camera motions. Depth images are also captured for original sequences. Then we use reconstruction systems such as bound fusion to capture the 3D model, camera trajectory, and speed. Meanwhile, it is easy to control the camera motion speed by using acceleration rate lambda. For example, when lambda is 2, we then downsampling the original image sequence to get a sequence with only half image number. Faster camera motion speed will generate a blurry image, so we further blurring the image by simulating the camera imaging with 3D model, camera trajectory, and speed. Finally, we get synthesized image sequences with faster camera motions. Existing image blurring methods, whether use a blur kernel or convolving a sharp image, or directly integrating sharp image of high FPS video to synthesize blurry image. Different from these two methods, we get more realistic blurry image by simulating the camera imaging during the image exposure time. Firstly, we use lambda to get accelerated camera motion speed, and we acquire the camera positions during exposure by the speed and the trajectory. So then we use the 3D geometry of the capture scene and the color information of the image sequences, as well as the camera motions during the image exposure, to finally synthesize blurry images with different lambda. Then we use our synthesis method to generate dataset. We create a dataset based on real image sequences recorded or directly picked from public dataset. A real slow sequence will have a real slow sequence has 9 fast synthetic sequences, which can be used to study the performance of video-based method to judge whether a method is robust to faster camera motion or image blur. Also, images with and without blur can be used to test image-based method. In this work, based on our dataset, we evaluate several mainstream methods of 2 relevant tasks: visual SLAM and image deblurring. Image deblurring. This page shows the performance of different deblurring methods in different blur degrees. In this plot, most methods have the same phenomenon, that the deblurring ability degrades severely as the blur degree increase. The reason is that the severe image blur caused by the larger blur kernel is much harder for a deblur method to estimate the blur. We then, as for the SLAM tasks, we evaluate 3 methods: feature point-based method, direct method, and ICP method. Here, we choose ORB SLAM 2 to represent the feature point-based method in our experiment, and we close the loop closure function for the better evaluation of the feature checking as well as the camera pose estimation. In part A, the solid line represents the result of sharp sequences, and the dotted line represents blurry images, and the ID of different lines is the acceleration rate lambda. The plot B shows the repeatability of each sequence belong to the one which is converged at plot A. The repeatability is also the ratio of the successfully checked features between the previous frame and the current frame, which measures the performance of the feature checking. This plot indicates that the robustness of the feature checking method is affected by the camera motion speed, and also it will be affected by the image blurs. As for the direct method, we evaluate LSD SLAM, SVO, and DSO. The table shows ATE-IMSE of 3 direct methods on sequences with different camera speeds and with or without image blur. Each value is averaged over 5 runs, and the minus indicates that a method is failed in a sequence. Box plots at the bottom shows the checked pixel or patch numbers and the average photometric pixel photometric errors of each frame. The blue and red boxes alternately represent the results of sharp and blurry sequences, and the x-axis represents the acceleration rate of each sequence. This result shows that the direct methods are also affected by faster camera motions. But comparing to the results of feature point methods, the image blur won't severely degrade direct methods. One possible reason is that because of the similar camera speed between two consecutive frames, the blur degrees of the two frames are close to each other. Then, the intensity of the checked pixels are also approximate in two consecutive frames, leading to the acceptable photometric errors in direct methods. For ICP algorithms, we found that the ICP cannot accurately check the camera once the sequence speed exceeds a threshold. Besides, by comparing the above three SLAM methods, we found that the ICP method is more sensitive to the camera motion speed. The reason is that during the checking of the ICP method, the information of a previous frame is directly acquired from the map, while the bad mapping caused by an inaccurate convergence will severely affect the following camera tracking, leading to the bad IT of the ICP method. That's all. Thanks.